I have to be extra careful to check that the recording started back up because one of them earlier this week did not. And it was a class with only one section, so it's just gone. Fortunately, it was on number theory, which a lot of you remember from the architecture class, but still, nonetheless, it would have been nice to have had it. All right, we last left off when we were talking about email servers, and I want to go over something that is oftentimes a point of confusion for people, and that's sort of what's happening with Gmail. How does that basically work? So let me open up my stuff here. I'm hearing some crazy echo stuff, so I think it's probably just a bridge glitch from joining. Okay, but it keeps having to investigate. All right, there's these cables out of the way. How did I end up with this cable nest this morning? All right, so you have SMTP servers talking to each other. Let me make this a little bit bigger. And let's say this one is uofh.edu. And I'm going to try to send something to rice.edu. So there are two SMTP servers involved, and I have a user agent program that is running on my PC. And between the user agent program and the web server, which is really an email server, I'm going to either run POP or IMAP. And that protocol has nothing to do with SMTP, and it only runs between the user agent and the email server. I should have said web server a minute ago. It's an email server, simple mail transport protocol. So if I send a message to someone at the other university, the server that is normally willing to handle that for me is the one that's associated with my email address. So if I have kblong@uh.edu, then I can build a message. I can send it to this SMTP server. Since it knows who I am, it ends in uh.edu as well, and I'm able to authenticate. It will accept the email message. Now its job is to figure out where to send it. So it will look up a DNS record for Rice, and we're going to learn what DNS records are today. But it will look up in a directory service the email server for rice.edu, the one that will accept incoming emails and the one from which outgoing emails should be expected to be arriving. And it will open a connection using SMTP and deliver the message. Rice.edu will check to make sure that the email message, which purports to be coming from someone at uofh.edu, is in fact coming from the server that they also look up in the directory service to make sure is this machine. So both sides do some checking, first to figure out where to deliver it, and the second one figures out where it should be coming from. If both of those things match up nicely, then both servers are happy and the email gets exchanged, and here it sets. So it will wait until I connect later in the day. Maybe I have it pushing to my server, maybe I have it pushing to my user agent on my phone, and I get an email over here. So let's say this is klong@rice.edu, which was my old email years ago when I was there. And I'll be running POP or IMAP here as well. So what's the difference between the two? One of the things IMAP did that was a big leap forward is it allows email to stay on the server, doesn't require that you pull it down. So therefore, you can read it from more than one place. You can leave it on the server. It allows you to have folders inherent in the IMAP protocol, and it keeps track of the status of messages. So if I also have a user agent on my tablet, and I am reading something on there, if I read a message and I mark it as, open it up, my rule is after opening it, it's instantly marked as read. I've seen some email servers which let you set the amount of time it needs to be open, like after 2 seconds of looking at it, it's marked as read. Then it will be marked as a read email everywhere. And I don't mean RED, I mean, of course, it has been read. So that's a huge advantage. And if you delete it from one, it will delete it from the other. All right, so this is the basic structure, assuming that the user agent is actually running on your device. So what happens if you have a third email server, and there's millions of them, but what happens if you have a third email server here, and it sits at google.com. So it's my Gmail server, and I could make it gmail.com if I wanted, but you get the idea. So there's SMTP running on here, and it has millions of users' accounts. In fact, there's probably lots of these servers, but we get directed to a nearby one whenever we try to connect, and any details, any complications that result from Google deciding to spread this out over more than one are their own. We don't have to worry about that. So there must be a user agent, right? So there has to be one somewhere over here. So I'm going to draw a user agent. So the question is, where is that user agent running? Because what I'm looking at the email on over here is, let's say, Firefox. This isn't an UA at all. This is a browser, a web browser. It's not running SMTP, nor is it running POP or IMAP. It's running HTTP, as all browsers do, to a web server. So let's say that Gmail has an Apache web server, and I have a Firefox browser that sits on my computer at home. It could be a Gmail app running on a phone or something like that. So what's the connection here? I will still run, let's say, IMAP from here. And they do give you the option, if you want, of attaching directly with a UA of your own on your own PC. And you'll run IMAP on this one as well. But normally, if you access it through a browser like most people do, these guys connect to each other. They're all part of this constellation of SMTP servers. So they all are checking each other, getting along well. Users are connecting with user agents. There must be something in between. So do you remember how last time we talked about most web pages are built on the fly? They're not actually stored on a hard drive someplace and just waiting for someone to open them up. They're actually built in real time. So what this user agent will do is crank out an HTML page, and it looks like Gmail. But each row, which looks like an email message, is nothing more than a hyperlink, like a link on the New York Times page, for example. It's not as colorful. It doesn't have lots of images. Maybe or maybe not it has ads on it. But it's meant to look more like what we expect an email client UA interface to look like, which is rows of emails, list of folders, the ability to compose, forward, delete, and some basic things like that. So it will generate this HTML on the fly and hand it to this Apache web server. And the Apache web server will use HTTP and deliver it to me, where I will render it over here in my browser, and I have folders over here, and I have the messages here. And whenever I click on one of these messages, it does what we saw Amazon do and JCPenney's do in the homework, and some of the other sites as well, like the New York Times. It uses a combination of cookies and URLs to inform the Apache server what I've just clicked on or what text I've just typed, and it can be enhanced with Java applets or other pieces of code to try to make things work more smoothly or animate them in a fashion. But if you're ever on a really slow connection, sometimes you'll even be asked by your browser, would you like to switch to the HTML-only version of Gmail? And you may see that request. So it's definitely going over this. And when I've clicked on that link and it's ready to go back, of course, it just goes in the other direction. It goes back to the user agent. It pulls the information out of this HTML, parses it out of the HTTP message, and the user agent then interacts. So the email server thinks that I'm here, and you think you're basically here. You believe you're probably talking directly to the email server. But this is another great example of how we've decided that we like the browser so much to be used as the interface for everything that we do that we have very thorough, working, well-designed interfaces that sit on top of even things like email. And we're totally comfortable using that as our interface. It has drawbacks. One of the drawbacks is if you get on the plane, you can't read your email anymore. There's no local cache for it as well. So what some people still use is they still use a regular email client, and they will interact with Gmail or Hotmail or Yahoo or whomever you use that way, right? And so you can absolutely use those regular UA clients to open a connection to Google. After all, it speaks IMAP and POP, just like all SMTP servers do. And these servers do some other things for you as well. They will go ahead and pull email down on behalf of you from other servers. So I have accounts on all 3 of these sites, but I don't want to have to log into 3 different places to read my email. So one of the things Google will do is it will go and fetch my email as if it was the user agent for me and pull it back down and blend it in with my other messages. Or maybe let me segregate it by the account name I've got. And I can still use this one window to access this collection of emails from all the places I've got. That usually works great, and the other email servers are more than happy to dump the email off, and now they're stored at Google. Right? And so now what happens if I want to respond to one of those emails? Well, they're not sitting on U of H's server anymore. They're sitting on Google's server. It's not just opening a window to U of H. It's actually retrieving the email messages, and now they're sitting on Google servers blended in with the others if I want. If I want to compose a message as if I'm at uofh.edu, that's where you can get into trouble. uofh.edu may look and go, you know, you're not where I expect you to be. It doesn't really look right. You're passing through an intermediate domain, and it looks to me like you're not really directly connecting to me. It looks like you're having a relay agent handle this for me. I noticed this because the header of the email contains those details, and I'm not comfortable doing that. So I'm not going to let you author an email as if it came from U of H when in fact I can see that you're behind an SMTP relay server someplace. So this becomes an issue. All right, so email, like we saw last time, is just regular text. You could telnet to a server. We also looked at a place that will let you test email. I think one of the other sites that I remembered the name of was something like Mailcatcher. And let's see if I can find that. That may be the one we looked at last time, but I'm not really sure. No, this is a different one. Okay, so this is one where you can basically pass email through this. It will grab everything that's going on, and it's a very, very easy SMTP server, but it's there to test. So it will not do some of the authentication checks. It's open source software, and it allows you to check port settings, and if you do run WebSockets, which was one of the HTTP 2.0 speedups we talked about, then your mail will appear instantly. It runs in the background for you. So there's some really cool stuff people have done, and I may give you guys an exercise to do one of these things instead of one of the socket assignments, because this is a realistic thing that you might actually need to do, because it's very difficult to test SMTP servers without sending actual mail around to people. And they don't like it, and all it takes is marking it as spam a few times, and you end up on a blacklist of spammers, for example. So there's some real innovation that people come up with to try to get around some of these problems. All right, so like we said, you can try this. I don't think this will still work. We can give it a shot. It's kind of fun if it does. You know, why not? Extra.cs. And I think he took this down long. Oh my God, I can't believe it. It actually still works. That's amazing to me. So let's see if I can say, hello, let's say kblong@uh.edu. Okay, it did it. Mail from, that was an incorrect message, by the way, but let me see if it'll do it. Okay, about the :uh.edu. I don't have a password, so I have absolutely no idea what I'm going to do at this point. Receipt to kblnhou@gmail.com. Cannot find your host name, so I'm going to run into trouble. But this is kind of funny because this probably shouldn't still be opened, because it's not doing much in the way of authenticating. You'll notice it never asked me for a password, for example. So that's a little bit of a problem. So we'll quit out of it, and we'll say quit. All right. So I got to figure out why that's still up and running. It's not mine, but I expected a lot of things today. That was not one of them. This hasn't worked the last few semesters, so that's why I'm really surprised, a little intimidated that it's still up and running again. Okay, so SMTP uses persistent connections, unlike HTTP, so it will leave a connection open until you sent all the email you want and you received all the email you want. It uses basically some special characters to determine when you've reached the end of an email message, and everything is in 7-bit ASCII. So if you put a binary file as an attachment, like you're going to send somebody a little MP4 file as an email attachment, better be small, first of all, but it's going to get converted from whatever that binary file format is, which is proprietary to MP4, into rows of 80-character human-readable hexadecimal ASCII 7-bit characters. No crazy special characters, no invisible control codes, nothing like that. So if you've ever opened the door accidentally in the middle of email when it's busy sending something, you'll see all these rows of text. And it's a push protocol as opposed to HTTP, which is a pull. So you sit and wait for, mostly, for you to get the idea in your head that you want to look at a web page, and then you will open a connection to that server and pull it down. That's a pull model. You can have web pages where they will continue to push data to you once you've established a connection. A really good example of that would be Click to Houston's radar maps. They'll push a new copy every 30 seconds to you, or weather.com will have things like that. And I haven't checked these in recent times, but people change their websites constantly. But those are prime candidates. Those are ones where I often see people pushing content to update kind of a severe weather map, for example. Whereas as SMTP, typically it's a push model. As soon as one SMTP server has a mail message they need to deliver, it gets antsy and wants to immediately push it across the internet to the other SMTP server. And if it can't do it, it starts complaining. So this is why sometimes you'll get an email message that says, I've tried for the last 12 hours to deliver an email message to this user, and I've been unable to deliver it to their SMTP server. I'm going to keep trying, but I wanted to let you know. And I'm like, what do you want me to do about it? I don't know the person that runs that other email server. Like, deal with it. So hopefully it will come back up, or whatever the problem is. But I've had plenty of email that just gets thrown back in my face. You can send multiple parts of an email message in a single multi-part message, so like the email and all of the attachments, for example. So there's a header which is more robust than what we've talked about with sort of other types of protocols that we've hinted at. We haven't really looked too deeply at any headers, but we've seen a few block diagrams of places to stuff information. Email headers can be arbitrarily long because they can timestamp and keep track of where things have been going. The actual internal mail message itself is something where you'll keep track of who the original user was and timestamps and things like that. So it'll have the usual to, from, and subject. SMTP does have some messages that it wraps around these things as well to kind of keep track of what's going on. But when people ask you, can you forward me the email so I can look at the headers, if you're having a problem, that information is very useful. It's also a big hint if you think if you think you're being fooled with an email message. Definitely worth looking deep in the headers to see if you can find hints like, why would it be passing through that server? That doesn't make any sense. We've already talked about this, but here it is in summary again. POP and IMAP are the two user agent protocols that speak to servers, and we use HTTP as often as we use either of those as the window into the user agent that Google's running. So the user agent and the web server are both running next to each other, maybe even in the same data center. Certainly possible. So here's an example of a POP3 protocol. It says, all right, I'm ready. Here's my username. Here's my password. All right, you're successfully logged in. Give me a list of my emails. You have two. The first one's 498 bytes. Second one's 912. Give me the first message, so it dumps it at you. You know that it's done with sending you that message because it gives you a period by itself on a line. And now that you've got it, you've stored it, you've put it in your own local email queue, you tell the server it may delete it from its repository. And now you're ready to retrieve number two. You'll do the same thing. You'll download it, and then you'll tell the server you you can get rid of it. You can delete it now. So you can just read through one of these things, and you might have to guess what this means, but it's not that hard, especially if I showed you the rest of the contents. And you'd see that the second one was twice as long. Oh, it must have something to do with length. So POP3 was an old style message where you pulled things off the server as quickly as possible to help the server manage storage. And you had very small quotas. If you didn't show up often enough, email would get refused. This might cause one of the messages I mentioned earlier about someone else not being able to deliver to you, and you're expected to pull things down quickly. So you really had to stay on top of your messaging. Storage was extraordinarily expensive in the early days. One of the more popular email programs was called Profs, Professional Office. It was IBM's email service. It was extremely full-featured, very well designed, very reliable, and ran millions of email accounts on IBM mainframes for people. And it's what NASA used throughout when I had a summer job there. So people may have different architectures for doing this now. They may do more of it over the network in a different way with TCP, but don't think for a minute that the first spam message didn't follow the first email message by about 5 seconds. We've been all over email from day one. We've done a good job at it. It's also stateless across sessions, so if you want something, you better download it. IMAP, on the other hand, allows you to organize, as I mentioned, and it keeps unique IDs of messages as they move around. I just wish contact databases worked as well as email systems do. They don't. It's a constant frustration. All right, so we're done with email, and we're ready to move on to one of the most important services offered on the internet, which is the domain name system. You'll hear some people call it the domain name service. It doesn't matter if everyone uses the shorthand anyway, which is DNS. So what is DNS, and what does domain name system mean? Well, you remember domain names we talked about. If I have a name of a host like labserver1.cs.uh.edu, this is the domain name. This is the fully qualified domain name, or the host name. So this points to probably a specific server, but not necessarily. It does need to be something that I can reach. And I like using names like this because it's easier than remembering the IP address that goes along with it. But someone has to convert this to an IP address. Who does that? Well, DNS is the database that keeps track of that. So the administrator who issues this name makes a decision about whether this is going to point to a device that's newly added to the DNS database, in which case it will be the first one in there with this IP address in my local DNS, or is this a nickname for some other system that's existed before, in which case this IP address not only exists, but it probably appears in the DNS database already with just another name. So you can have multiple names pointed on here, like students.cs.uh.edu. That can be one where students have their files. You could also have it be www.cs.uh.edu, and that can also point to the same IP address. But the official name, the first one that you added, let's say it's this guy here. And these are just nicknames. They're aliases for the real one. And we add aliases all the time because usually one of the aliases you add is www. You just tell the domain name. Anybody tries www followed by the name of one of these things, just go ahead and send them there. Just put them in port 80. So this directory is similar to a telephone directory. I can have multiple people's names in my house, all with an entry in the telephone book that point to the same telephone number. Right? So I also can have numbers that get added for the first time, numbers that get removed. Whenever somebody adds a telephone number, like you have a telephone line activated as part of your DirecTV service, for example, then that gets added automatically to the directory system. It used to take a while for the paper to move around, and now it's all done automatically. So it's very similar to that type of system. It's needed because Internet hosts actually have 32-bit numeric addresses, and we write them down in these little groups of 4 numbers. So this is an example of an IP address here, but it's 32 bits long. So each one of these is an 8-bit binary number that I've just, for my convenience, wrote down as 4 decimal numbers. The name is what's used by us, and so you map these things together. So DNS is a distributed database. It's implemented as a hierarchy, so we'll see what that means. And here's what's really a source of endless fascination to me over decades. It's an application layer protocol that programs are expected to call on themselves. You would think when you sit down at your computer and you type into a browser, google.com, that you build a socket request and make a call to, let's say, the TCP library, and you pass it the fact that you would like to get to google.com, plus what other payload and what other options you may have. And it works its way down to the IP layer, which is layer 3 network layer. And IP is the one that looks at IP addresses. It's where IP addresses are used to forward things. It's where a table is kept of where ranges of IP addresses can be found out of which of my network ports, if I have more than one, like a router certainly would, out of which of those ports would I find these ranges of addresses. So you would think that this google.com would get converted to an IP address here. It doesn't. In fact, you can't even make this call unless you feed it the IP address. You must know the IP address before you even get to the transport layer, before you get to layer 4. So up here in our program, we have to stop what we're doing. We have to go make a call to this other program called DNS, which is name server resolve in lots of Unix systems. That's the name of the function. So you have DNS that gets called. You pass it google.com, and off it goes. And it will make a journey that will blow your mind, and we'll come back with the answer. And once you have the IP address, then and only then may you begin. Meanwhile, the user's waiting this entire time. They've already hit google.com and hit return. They're waiting on the web page. So this all has to happen. And then you have to go open a TCP connection. So it's not going to send any of your data down to Google until first it goes down and all the way across the internet to ask permission to send something. And if it gets it, the handshake, then it comes back and does that. So there's some real complication to this, and it's fascinating to me that the OS doesn't really do anything to help application authors manage this thing as well. So it's an application layer protocol. It's a core internet function. The internet will not work without DNS. It's a constant source of attacks. We find that people are able to successfully attack and degrade or disable DNS, large parts of it on a regular basis, taking down like a third of the internet, or the eastern part of the United States, or most of Latin America. And I've experienced all these things within the last 10 months. So it's a constant source of attack, and so for this reason, it's highly distributed to try to minimize its vulnerability to these types of problems. All right, so we're going to spend some time getting to know DNS in quite a bit of detail in this class. So the services translate host name to IP address, and like I mentioned, they also do host aliasing. So any nickname you want to give, a second name, a third name you want to give to a host, those are aliases. The official name is called the canonical name. DNS not only keeps track of the IP addresses of servers and hosts just in general, but it also keeps track of special types of entries. One of them is an MX entry, which is the name to IP address translation for the host that you've set aside to run email, specifically the one that's going to run SMTP for you. So if you have a domain name from GoDaddy.com, like xprof.com, then you're going to be on a server with 100,000 other domain names, all serviced by the same single copy of SMTP email server software running on this server. And the next 100,000 domains will be on the next server, and so forth. And they'll back each other up, but it doesn't have to mean you buy a server and install it to run email. You just need to point this entry, this MX record, to some IP address whose owner is willing to handle SMTP messages on behalf of your domain. That's it. So when you buy a domain name, you usually don't even think about this. It's completely transparent because it's included as part of the service. You get access to an MX server. You also get access to a DNS server as well, where you can insert those entries and make a record of what you've just decided to do. There's also A entries, which are some of the primary ones just to map IP addresses to domain names, and there's some other ones in here as well. So mail server is a good one. It's also got some interesting features that people have sort of figured out. So things like mail kind of got crammed in after it was thought of. And it's a DNS is widespread. Everybody uses it. Every host has to know how to use it. So since people usually want more than just like an IP address in the morning, why not modify these services so that they are able to answer the next 3 questions you're about to ask if they've got the information to do it, like what's the IP address for google.com, and oh, by the way, where can I send an email to those guys? Load distribution talks about something interesting with DNS where we can actually go take a look at how this is going to work. And I think I have a link here for you guys, so I'm going to skip ahead. Right now I'm on slide 4. Okay. I'm going to skip ahead and pull up something now that would normally come later. Let me drag this in. Let's go to my browser. And I'm going to pull up the DNS entry for google.com. And what you may notice is there's a whole bunch of things that come back. Now, if I pull up the name for kbell.com, it's going to give me the email record. Oh, they don't like it. They couldn't find it. Let me see if I can find another one here. This is probably expired also. It's probably not going to. Yeah, so I buy domain names all the time, and I just fail to update them with all the different record types I'm supposed to have. How about this one? This one should still exist. Okay, so this is kind of typical. This is a domain that's parked at GoDaddy.com. And it's got a primary and a backup server to handle email. GoDaddy names their domain for email secureserver.net. That is supposed to make their users feel better. They run a good shop, from what I can tell. I think GoDaddy, I don't think I've ever had real issues with these guys. So I'm looking at the MX record for GulfCoastShots.com right now. And I got back 2 entries. Each of them are 60 minutes long, meaning once I learn this information, go ahead and store a local copy of it in your own local cache for an hour. And after an hour, throw it out. If somebody asks for it again, come and get it again. And we'll both just make sure that this information hasn't changed. If it does change during that 60 minutes, we're in trouble because there's no way for me to know. And there's a lot of IETF work to try to fix that. All right, so let's do a regular DNS lookup now, and this one's even simpler. So this is a single entry. So if you try to connect to this domain name, your TCP connection will have its function call filled in with this IP address, because when you call DNS with this name, the DNS database will give you back this number as the answer. And now you've got the number that you need. Let's go back to Google. And I want to make sure I'm looking at DNS here. By default, when I went to that URL, it pulled up the MX record. That's not what you're going to want. You're going to want to look at the A record for google.com. So this looks like it's a single IP address. One of the things that would be interesting would be to get some of you guys to also look up a DNS entry for google.com right now at the same time to see if you get the same one. So I can drop the URL into the chat window if somebody feels like trying it. Now the one I'm going to give you, I think that's the right one. That's google.com. So that may pull up the MX record. It looks like it will. If it does, flip it over to DNS by moving this. And what I want to know is what IP address you get back. do you get back the same one that I did? And mine's kept down here in the history. So this site's nice because it also keeps a history of things I've done. All right, so I pulled up Google and I got one entry. And I pulled up Amazon and I got 3. And 2 of them are 176s and one of them is a 205. Okay, somebody got a 174 here, Oswaldo, 217, 174. You'll notice that's different than what I got. 172, 217, 7.238. So lots of you in Houston will get the same one. If there's anybody who's out of town today and watching this, or has a VPN open to some other part of the world, you can try doing it through another site, and you might find something a little bit different. Okay, so this person got something different as well. So it's going to be a little difficult for me to nail completely the explanation because MX Toolbox is sitting in the middle here. And I don't know exactly how MX Toolbox is referencing DNS servers, but I'm going to walk you through some common scenarios that explain why we get different IP addresses when we ask for this information. And one of them is what was on that slide before we moved. And what was on that slide, you'll remember, was load balancing. That was the bullet that was on slide 4 before we scrolled all the way down to here. Okay, so let's say I have a DNS database. And one of the things I would expect is that both Google and Amazon would have lots of servers out there. So why would I get just 1 from Google and I get 3 from Amazon? Why wouldn't, I mean, Google's bigger, right? Aren't they doing more stuff on the internet at any given time? That's confusing, maybe not. AWS is pretty big, but why would one of them have 3? What's going on there? Well, this is a load balancing activity. So when the DNS database feeds a service, it's given a list of multiple entries, it will round robin the answer to the person that's making the inquiry. So if I ask for the DNS entries for Amazon.com once, I get them in this order. If I ask for them again, depending on how long has passed and depending on how many there are, you can see this rotate around. So I got the same thing twice. Different servers may do it differently. We've gotten more sophisticated, but that was an early way of load balancing. So if I have multiple servers, one way to make sure everyone doesn't get the same answer and all gang up on one side is to have DNS first give the IP address for this one, and then the next person that asks for the IP address from the DNS database is going to get this one and this one. So you kind of round robin and spread your traffic load out among these 3 servers. So that's kind of built-in load balancing with DNS. DNS was not invented as a load balancing tool. It was invented as a telephone directory. But this would be like calling up directory assistants and asking for the phone number of a airline, and they give you a different one every time. What really happens when you call up like the 800 number for United Airlines, they will dispatch your phone call to whichever call center has space right now with a similar type of service inside the phone network. They will not ring just one place. They'll have that number mapped virtually to lots of others. All right, so that's one reason why you'll see multiple entries here. It's not just for backup. Okay, so then why does Google not have one? Why does Google just have one answer? Another thing that DNS can do is, because your PC, when you're given your IP address in the morning, because it's given a bunch of other things as well, like the network name that you're supposed to be using, like you learned, for example, that you're on UH.edu. You wouldn't have known that otherwise. And you also are given your IP address, and you're given things that we'll learn more about, things like subnet mask and stuff. One of the things you're given is the list of DNS servers that you're supposed to be using. And you don't even have to type it in. So if I pull up my network preferences on my Mac, and I come down to advanced settings, and I go to DNS, this is the one and only IP address of a DNS server. It's kind of dangerous, that I was given when I connected this morning. And the domain that I was told I was a part of was monterey.etesm.mx. And so if I want to find a host on here, like I go up to my browser and I just type in registrar, for example, it will guess .mty.etesm.mx. That's its default search domain. But people change their DNS services all the time, and yours will probably not be these same numbers. This is a private IP address. Lots of people use private network numbers, so we could have the same one, but it's most definitely not the same server. No one else on this call is using this server but me right now, and you may be at a place where you're the only one using the one that you've got. But sometimes people don't like the DNS server that they've got because it's too slow, or it's pokey, or it doesn't give out the best possible information. So they will hard code in a different DNS server address. And if I can remember what it's called, let's see, Cisco DNS service. I can't remember. We bought this company, OpenDNS. God, you think of how much simpler could the name have been? Okay, so OpenDNS is a company that has a very high quality, high speed service for DNS, a really good reputation, and Cisco snatched them up. These companies don't last long on their own. Somebody grabs them. And one of the things they do is publish DNS services that they're welcoming you to use down here at the bottom of this page. So you can use this DNS service if you want. Google also has public DNS servers, which are, I think, like 200, I want to say. Here's one, 1.1.1.1. I mean, that would be, how cool was that IP address? It's a real IP address, by the way. But if that's actually one that they're using, you can try entering that as a DNS server and see what happens. Okay, so this looks like it's legitimate. It says it's real and more private and faster and all that kind of stuff. I'm sure it's all of those things. So back to, why does then Google just have one entry in the database? Well, one of the things they can do is coach these servers to give a different answer depending on where you are on the network. So what we're seeing up here in the chat window with you guys is your different places on the internet, and when your DNS server goes to see what the IP address is, sometime earlier today, someone gave a different answer. And they did that because they want your traffic, when you try to actually connect to Google, they want you to go to a different destination on the internet. They may want you to go to a data center in San Antonio instead of me, a data center in Rio, for example. So they're going to give us different IP addresses. And they can do this on the fly if they've got, you know, the strength and the CPU speed and the confidence to do it. They can get rid of all of the duplicate round robining in DNS and just be, you know, super confident that they're not going to fail to update these things, and because if they do, everyone's going to just end up going to the same one. The other thing that's interesting is you'll notice it has a 5-minute expiration. So this is .238. So let's go do it again. It's been 5 minutes. And see what I get. I got the same one, but I had to go pull a fresh copy of it because it expired. So this has just a 5-minute time. Some people have a 0 TTL. So if you are a mobile user, constantly on the move, moving around, it's not a great person to be if you are trying to run a server that you want people to get to. It's better for people if you stay put and you stick in one place so your IP address isn't constantly changing. That would be nice. And then people could look up your DNS entry, cache it locally for like an hour, and not have to go beat the brains out of the DNS server every single time they want to open a connection. Think about the New York Times webpage. It had like 100 objects on it that were spread across 20, 30 different servers. Every single one of those would require a DNS lookup. And so you want to be able to cache those after you've learned them the first time for each one of those servers that we saw. And if you set your TTL to 0, it will never be cached. So why do that? Why have that? Well, if you are trying to remain reachable through a known name, like Kevin's laptop .textprof.com, for example, right? So that was a domain I registered to show the class how to do it once, and so I think it's clear now. So if I want this, the implication is I need you to always know where I am. So if I am at Starbucks and I get an IP address and I update my DNS entry and I leave it there for an hour or something, then what's going to happen in 5 minutes when I've left Starbucks and you try to get a hold of me there? It's not going to work. Here's one that's also even shorter, 60 seconds. That's almost a 0. So what does 0 actually mean? It means you better have someone who's got a DNS server who's willing to answer every request that comes in, no matter how frequent they are, and you're going to pay them to do that and to drop some software on your computer, and every time it sees that you've moved from someplace to another on the internet and your IP address has changed, it's going to update that DNS server that they're running for you. So it's a little widget that will automatically recognize every time your IP address changes and immediately update this DNS database. So 1 second later, if somebody comes and tries to connect to you by typing this into their browser, which is going to cause their browser to go run NSResolve, and it's going to try to resolve this, and they're going to find it's not in any of the DNS databases where things are cached, and they end up having to go all the way back to this DNS server, they will, which will take all of a few seconds, they will find the current up to the second IP address for me and will be able to connect. Now, if I move in the middle of the connection, then they've got a problem. But that's the idea. It's great for mobile users or people that just don't want to pay for a permanent IP address. It has to be a public one still, but it doesn't have to be static. It can be dynamic, and sometimes that costs less with ISPs. Not usually, but sometimes. So people get really good at managing how people know where they are by paying really close attention to how long they let these DNS records survive in a database. Okay, so there's other junk in here that's kind of interesting. We'll touch on some more of it as we kind of go through this. So why not centralize this? It's kind of an insulting question. It's never going to scale. So single point of failure is the biggest problem, and people do attack DNS all the time. There's some bad habits people use, and so before we look at the hierarchy, I'm going to set one other thing up for you guys. There's a company called Dyn.net. They had a very famous outage last 2 November the 13th ago, and it took out lots of countries' internet from their major ISPs and a third of sites on the eastern U.S. And I actually may have the article in Wired. Let me see if I can find it, because it had a Twitter diagram that went with it that kind of will show what I'm talking about. So let me see if I can find this in here. Dyn.net, Durham Data Center. All right, let's try this. DDoS attack. How a tiny error, GitHub, dorm room, not Radware. This is, maybe it's in here. I don't know. Let me go look one other place. I do want to find the diagram because it was pretty good. Wired Dyn.net DDoS attack. Okay. It's in this article, but it's not the article. So massive by Dyn. Here's the other article in 2016. Okay. Why do I not have this in Evernote? So that's ridiculous. So let's add it in there so I don't ever have to waste time again. Wired. Okay. Done. So they had a massive DDoS attack by just taking down these guys' site. And there's some Twitter links in here. But I spent enough time on messing around with this kind of right now. They may have kind of a Twitter view of it. So they may have hidden it because it's kind of embarrassing as well. But these guys were pretty open. They did a good job of like letting people know what's going on. And as you can see now, they've teamed up. I guess they've been bought as well. Maybe they've they've been picked up by Oracle. So what these guys do is run DNS servers and deal with all the updates, deal with all the authentication, and they push the content out to other ISPs. So Telmex is a major provider. They're like AT&T in the US. Both of them run DNS services. And what they do, and lots of other people do, is they buy their DNS services from Dynet. And so all of the DNS servers around Telmex are fed data by this Dynet service. And if it goes down, you're okay for a little while because you've got lots of things that are cached, right? So you may have things for 60 minutes, you may have things for 30 minutes, you may have things only for 60 seconds. We saw examples of all those. And as soon as those expire, you go back and try to get an update, and you can't. That's when the problems begin. So as the minutes tick by, larger and larger groups of users can't get to where they want to go. And the irony of this is the most popular sites are the ones that have to spread their traffic out over multiple locations to handle the load. And those are the ones that typically want to guide every user every moment or two to the right best place. So they never leave DNS entries in there for more than 60 seconds or 5 minutes or 10 minutes. So they expire almost immediately. So the irony is the sites that you want to get to the most are the first ones that you can no longer reach because their DNS entries expire. So this caused a huge problem because lots of users depended on their ISP to get to the outside world. If you knew the IP address of where you were getting to, you were golden. If you go and grab a static copy of the DNS database and just take your chances that things don't change very much in any given month, then you can stuff your own DNS database with knowingly expired entries that are probably still accurate. Or you can go to OpenDNS or Google and use their public DNS servers and just go to your own PC, sitting wherever you are, instead of using your ISP's local DNS server, just jump right over it and go out onto the internet to Google, for example, or to OpenDNS's or anyone else's if you want. Or call somebody up and go, hey, what's the IP address for google.com? Would you mind telling me real quick? And they'll do it. The problem is when you get back a web page like the New York Times, what we saw in that web page were lots of URLs, not with IP addresses in them, but with names that also had to be resolved with DNS. So it's pretty much crippling to have DNS go down. And this one was one that started at Friday, October 21st. I was giving a talk when this happened, and my students started getting nervous. I was 450 students. I was like hearing a murmur, and I stopped. I'm like, what's going on? You guys are all like, and they're all checking their phones, and they're like, I was talking about DNS security at this talk, and they go, did you just bring the internet down? So they actually thought I had something to do with it. And I thought about saying, yes, I did, and you better be nice to me or something like that. I just said, like, no, what are you talking about? So anyway, it happened in the middle of the talk. The same thing happened again when I was giving a talk a few months later at U of H. Very similar, kind of massive DDoS-related intervention by law enforcement was taking place. And so, the next time I gave a talk, I warned everybody, and they're like, just please leave. Please don't give the talk. We don't, basically destroyer of internet. So I've had some bad luck in that regard. Okay, so we're finally ready to take a peek at the distributed nature of DNS. It's hierarchical. At the top sit root servers. If these go down, the world as we know it ends. There are 13 contracts, the last I checked, with 13 different companies who run the copies of the information that tells where to find the next level down. They do not keep a copy of all the domain names and their IP addresses. It is not the world's telephone book. It's simply a list of country codes and the number for directory assistance in every country. So this is like a world operator that you can call up and say, if I want to find the telephone number for a phone in France, who do I call to do that? And this root server will tell you the number to call to go and do it. So they will only do that, and they're only going to answer that question from other country operators, like, hello, this is the operator for Spain. Can you tell me who to call to get phone numbers for France? If you don't know it, you'll ask the root server. If you've written it down and you have it in your cache already, then maybe you trust it for a day or two. But that's what the root server does. So these keep track of where these other large critical databases are. The next level down are called top-level domain DNS servers, or just TLD servers. So what's a top-level domain? A top-level domain is anything that's after the last period in a host name. So for example, .com, .mx, .tx, .mil, .org, .co, .us, all of these are top-level domain suffixes. And each one of them maintains a DNS server. And the DNS server you can go to, and you will find one entry in here for every single .com. So the DNS server for .com will have all of those entries. All right, so let me stop sharing for a second because somebody's unmuted themselves, and I'm tired of hearing the paper ruffling, so I'm going to mute you. Okay, so that'll have all of these. So it will not have a list of kevinslaptop.textprof.com. It will not have studentserver1.cs.us.edu, but it will have textprof.com and amazon.com and google.com. So what is this entry in here? It's going to be the IP address of something called the authoritative DNS server for that domain. So if this is Amazon's, right here, what this is pointing to is a big Amazon server that is required by RFC to give an answer to any host that ends in amazon.com. It must have the entry or respond by going to grab it quickly. So in my case, server3.seattle.datacenter2.floor5.rack3.amazon.com. If it's something that people need to reach with an IP address, it will have an entry with the host name here and the IP address here. This will also have the MX record for Amazon.com, telling you where you can send email and where email should be coming from that claims to be representing Amazon.com. And it can have some records that face the outside world because they want people outside on the internet to be able to reach it. They will certainly have lots of entries in this database that these guys don't care about that point only to hosts inside of Amazon, like lunchroomwebcam.amazon.com. Well, that's not something you might want to look at on the internet, but inside the building you might, just to see how long the line is so you can kind of gauge when you want to go to lunch. Right? So something like that might be an internal one. But this is the one place the buck stops here. So that's an authoritative DNS server for a specific domain name. And all of the .coms roll up to one .com TLD server. All of the .orgs roll up to one. All of the .edus roll up to one as well, all over the world. All of this stuff is done redundantly. There's multiple copies of each of these things, but there's one concept. There's one node on this and one TLD DNS server for every top level domain. So where are these root servers? They're spread all over the world. That makes lots of sense. Here's a list of, and the last time I took a snapshot of this, of who was running them. Some of them are owned by universities, like the ones that start with the letter D, and I'll show you what that means. The University of Maryland, VeriSign, the people that build the credit card reading, chip reading machines at Target, they have a set of these. NASA runs one. The Department of Defense of the United States military runs one, and so forth. ICANN, the Internet Corporation for Assigned Names and Numbers, kind of runs the show. They issue the other ones. They run one. There's one in Tokyo, etc. So how can you see, what these things look like? All right. So here's the names of these things, and these are published to all TLD servers around the world, and they're to anybody. And this is a place to go and get information from a root server. It's public information. There's an IPv4 address and a very different looking number after it. Those are IPv6 addresses. So you can connect to them either way, and you can ask them a question. That's not terribly interesting to us. What's interesting is somebody has built a site that looks the same but ends in .org instead. And it's just information about these guys. So it's kind of a cool idea, right? It would be like having uh.edu and then uh.org tells you lots of things about uh.edu's network. That's kind of the idea. So we can go to rootservers.org and pull up an interactive map of where these things are and get an idea of what it looks like. And why didn't copy it right? Let's try again. There we go. So they'll have some news notices at the top, some IETF meetings that are going on. Here's a list of the various members that own these things now. A couple of these are new names, so somebody's gotten bought, something like that's happened. And you can see there's numbers and counts of these things. There's one in Hawaii, it looks like. Oh, French Polynesia. Okay, well, that's kind of interesting. And what about this one here? What's this one? That's Samoa. And that whoever runs that one also has one in the Russian Federation. So that's the Internet Corp for assigned names and numbers. So they put some in interesting places, maybe topographically, where people, they want to reduce the chance that people maybe get isolated, perhaps. But what we can do is zoom in on this map, and we can start seeing where some of these things are. Houston didn't have one of these for the longest time, and we finally score one now, which was kind of embarrassing. But we do have one now that's run by the Internet Systems Consortium. It doesn't exactly show you where it is, but they are supposed to register their latitude and longitude, and it looks like it's downtown. So it's probably a network exchange center. There's one in San Antonio. If you know much about San Antonio at all, it wouldn't surprise you, especially when you see the list of these up here, that this is a DoD one at Kelly Air Force Base probably, because the military uses the internet as well. There's some down on the border of Mexico. There's one in McAllen at the NASA Ames Research Center, and then there's a commercial one run by the Internet Systems Consortium as well. This is a major transcontinental fiber route for, among other people, Level 3. They just extended a massive new fiber run from Mexico through Monterey and up through McAllen and then on up into the United States. So my internet life and experience dramatically improved when that happened. It was hugely important. And there's even a couple of them here, including one where I'm sitting right now, the Internet Corporation for Assigned Names and Numbers. It was the very first connection to the internet in Latin America. Was in a building about 100, 200 feet from me right now. So U of H has had a very important, very early role in the internet as well. They hopped on it. Charles Chambers, our network manager, was all over it. So we've done well. He's still here. We have reason to be really, really proud of the presence that the university has on more than just the internet backbone, on some other ones as well. That's why when you trace routes from U of H, sometimes you see some kind of interesting sites along the way, like why does our trace route first go to Rice sometimes, or first go to Baylor College of Medicine? It's because of this other backbone that I'm talking about. Okay, so that's the idea. You can show who the specific operator is. You can get a map and see where things are. So I always have these slides in case the thing doesn't work for me. We've talked about TLDs, top-level domain servers, all of these .aero, .jobs, .museums, .com, .org. We talked about authoritative DNS servers. Those are the ones that provide the exhaustive list of publicly accessible host names and their corresponding IP addresses to anyone that wants it on the internet. So what you hope for is people ask for some of these things. The more popular ones are going to get cached along the way, just like web objects get cached as well. You can have a local DNS server yourself. It doesn't really belong to the hierarchy, but it's invaluable. You can have one in your own department. You will have more than one on campus typically. And this is what's known as your default name server when you are given your credentials upon first joining the network. So that DNS entry I showed you in my panel earlier, that was that 10 dot number, that came as an entry as part of my default name server. So it may or may not be the University of Houston's authoritative DNS server. Probably it isn't. So when a host makes a DNS query, if it doesn't have the answer in its own cache, on its own CPU, and phones maintain those caches and tablets, not just laptops and servers, if it doesn't have it itself, it will go to its default name server. If it's not in the local default name server, then that name server knows where to go and start climbing the hierarchy. All right, so let's walk through one example, and then we're going to do another one next time with this diagram. But I'm not going to use this diagram for now. I'm going to use a different one. And if I'm super lucky, I will find one that I used before. Not that one. Nope, I'm going to draw it. I can draw it, so why not draw it, right? It's not like I don't know how to do it. Okay, so here I am at, let me give myself a name here, kl.cs.uh.edu. That's the name of my computer on my desk. And I want to get to js.cs.rice.edu. In fact, I'm going to make it different because I want to make this a little more complicated. Let's make this one at etesm.mx. It's an educational institution, but they chose to get a .mx domain. So I open up a web page, and I type in www.js.cs.etesm.mx, or maybe I just type in js.cs.itesm.mx. But you've got a web server running on your laptop over here, and you want me to connect and see if I can pull HTTP2 code down. So I type it in, I hit return, and the journey begins. First place is I look at my local DNS cache, and I don't find you. So I look in my credentials, and I find I have the identity of a local DNS server. It's called dns.cs.uh.edu. And I ask it. My software knows how to go and do that. It knows how to go up here and ask this DNS server using the DNS protocol, send it a message and say, do you have an entry for JSCS.mx? And it says, yes, then great. I will make a copy of it. I will add it to my local cache, and then we're done. But that's too simple. It doesn't have it. So it's going to go up to dns.uh.edu. And this is my authoritative DNS domain name for uh.edu. So this is the one the world knows about as well. It looks in its larger database, and it has not seen anyone connect for a little while to this domain, so it does not have the IP address of the host, but worse than that, it also does not have the IP address of dns.etesm.mx. So it doesn't know who to go and ask. It knows this server has the answer because the authoritative server for etesm.mx must have it. So there's one other local in between here. So it mirrors what I have at U of H. And so we're going to see kind of how the rest of this plays out. So it does not know the authoritative address. So who can he go and ask? He can go and ask the top level domain server for .mx. But what if he doesn't know who that is? What if he's never connected to the TLD for MX since it was last flushed from the cache, or maybe ever? So he's going to go up to his TLD for .edus, who will go to the root server. The root server will know the IP address of this. It will send it back. It will actually send this address over to here, which will now come down to here. He will go and ask this TLD server, what's the IP address of this A guy? And I'm making the questions in blue and the answers in red, so let's stick with that. So then I make, not the right marker. Then I make my request here. It knows the answer already of that guy, so it sends the answer back. It's basically sending the answer back to here. That gets sent down to this guy. He then knows how to connect to this top level server and ask him for the IP address of js.cs.itesm.mx. And he must know. So without the help of the CS intermediate domain server, he sends this answer back, and I finally learn who it is. Now I'm able to actually make a TCP connection request over to here and do my handshake. And if I get permission, then I can open up an HTTP. I can send my HTTP message. All of that has to happen in the time from when you hit return on your browser to when you start seeing objects show up. So it's very fast, and it works because most of the time things are cached. So what's left behind after this as kind of a trail of evidence? Who has JS in their server? He does, and he does. Anyone else? No. All right, who has CS's address in their server, in their cache? No one. Who has, except this guy does, but he's always had him. Who's got DNS.itesm in their server? He does. I'm going to just call it .mx, and he does. Okay, who has the TLD address in their cache now? He does, for example. So you're sprinkling things around as things get cached, but we'll look at an example that's got numbers on it so we can kind of be methodical and kind of keep track of the sequence things go in. There's a couple of different versions of doing this. One's called iterative, the other one's called recursive, but we'll have some more fun with that next time. So we have a homework due Sunday. Don't forget, I'm going to try to crank one out. We're sort of, the homeworks are behind the lectures enough where I'm going to need to skip forward a little bit, but you do need some DNS exercises because it's something you're going to get asked on the midterm exam. So I'll prep you for that, but this is one of the topics that you're absolutely going to see again soon. Okay, let me make sure I don't have questions lingering around in chat. Destroyer of internet, muter of microphones. Yeah, well, that one's more. Oh, okay, awesome. Thanks, Larry. You found the statement on it. Excellent. Okay, so this is one that I need to grab. What I really want to see is the Dyn Twitter image showing DDoS outage. If I can get super lucky, bingo. All right. So this was bad. So this is what it took down at its peak. It looked like this. It was hacked home devices. This map doesn't look right. I'm not sure if this is the same attack or not. Let's see what the date is on this. Yeah, it is. It's the same one. So cool. Yeah, all right. Fun. Take care, guys. Have a great weekend, and I will see you on Tuesday in class in our lecture room. Bye, everybody. Talk to you soon.